Glad to be here.
All right, probably ready to go. We ready, Andrew?
We're ready.
Awesome. All right, man, today is going to be a fast pass over a lot of information. Each one of these things we're going to cover could have its own hour-long plus presentation as it relates to applications and limitations and optimizations. It's a lot of information, so we're kind of skip over some stuff at a pretty shallow level. I'll save some time at the end for questions. I don't know that we'll get to everything, but hopefully we make it worth the time. Okay. Today we're going to talk about dissolved phase pumping systems. My name is Jeff Immo. Been with Geotech for a very long time, 23 years. Been in the industry, another 15 on top of that as project manager and doing remediation. So a little background on this. I'll try to bring some context and maybe a story if it fits in to help illustrate a point. We're going to cover electric submersible pumps, pump controls, pneumatic remediation pumps, oil water separators, and air strippers. If you're not familiar with those terms, maybe you'll learn something. Dissolved phase applications tend to focus largely on hydrocarbon impacted groundwater, but not necessarily only groundwater. DNAPL impacted groundwater, chlorinated solvents, things that are heavier than water, landfill leachate collection systems, other pump systems, and effluent processing. If there's something in the water as a dissolved constituent, what we're going to try to cover today is what are the pumping options and what do you do with that effluent once you've pumped it. Okay. Key factors for selecting a pump. It's a combination of things. You know, there's never a perfect world in the remediation application. If you've got impacted groundwater, there's usually some other considerations. Things we want to make sure we take into consideration are temperature. Elevated temperatures can be very problematic, particularly with electric pumps. The electric rating for temperature on most submersible motors is about 84 degrees. So if what is being pumped is greater than 84 degrees, it could be problematic. There are some pumps that will approach 100, but depending on the flow rate and the pumping head, that may not be an option. Another consideration is TDS. Anything greater than 1,000 ppm TDS tends to be very problematic for electric motors particularly. It also becomes a factor when you get into pneumatic pumping systems, and we'll talk about that in a little bit. pH is another consideration. Anything less than 4 as a rule will generally be a problem in the long term and possibly in the short term. There's a situation where there was some dissolved phase at an Air Force base that shall remain unnamed. They had chlorinated solvents, they had a little bit of a higher temperature, they had a higher TDS, and the long story short is the cocktail made a very aggressive acid type environment. And stainless steel, particularly in electric submersible pumps, is only as good as the weld on the seams of the motor. And when you weld stainless steel, it changes the properties of the stainless. And in this acid environment, it would corrode and erode welds and cause a leak path of fluid into the motor. They were replacing pumps and motors about once a month. Now the question is that okay? And given the site conditions, that might be the only option. But from a budgeting standpoint, that could be really problematic while you're trying to explain why am I changing the pump once a month. We did find a 316 grade stainless pump that lasted 6 months. So given the project history, going from 1 month of operation to 6 months of operation was monumental. Again, aggressive site conditions, not all places are the same, but just something to consider. Gases, H2S, other things that might be released during pumping can have an effect on pumping rate, motor cooling, maybe even off-gassing on the effluent. So things things that may be problematic, and lastly, specific gravity. All electric submersible pumps particularly are rated on water, specific gravity of 1, but when you start adding TDS and maybe some dissolved constituents, if that specific gravity is greater than 1, the compensating factor is you'd have to increase the motor horsepower to allow for more cooling and to accommodate the higher specific gravity as it relates to the pump's ability to perform. Doesn't come up very often, but in cases where there's brine, for example, in the groundwater, gas extraction wells, for example, that greater than 1 specific gravity is a problem. So I don't know if you encountered that, but something to keep in mind. Electric submersible pumps. The nice thing about an electric pump is it's kind of like turning on the faucet. The water flows. As long as there's water and recharging in the well, the water will move through the pump and the discharge stream will be a continuous flow. There are pumps rated for less than 5 GPM and greater than 1200 GPM. So the availability of pumping head and flow rates in the electric pump line is vast. But when you start moving into greater head pressures and higher flow rates, you have a corresponding increase in the need for higher horsepower motors, which require more energy, bigger motor lead cables, and it can be a very substantial operation, especially if you have a production type well environment where you're pumping a lot of water into a treatment system. Could require a lot of energy. I've seen motors come through the shop here that are 40 horsepower. A pump that's got a 40 horsepower motor and a big pump end could weigh 800 pounds. So not exactly portable, but definitely an option. Electric submersible pumps give you operational controls. You can control flow rate, pumping level, on-off characteristics, a lot of variability in terms of interfacing with PLCs or other controllers that allow you a lot of flexibility in how to manage the site. There are pumps available 3-inch, 4-inch, 6-inch, and even greater, but those are probably the big 3. All of which can be environmentally retrofitted if they're not already manufactured as an environmental pump. And then there are some options to going solar. There are some pumps that are specifically designed as solar-powered pumps using windmills, solar panels, things of that nature. Or there are interface tools that you can incorporate with a standard electric motor to convert it to a solar-operated pump. Now, solar's got its own limitations. Generally speaking, if you're interested in solar, it becomes a gallons per day more than a gallons per minute because of, right, you have limitations in how much sunshine you have, how many panels you can place, and whether or not you have enough battery capacity to keep the thing operational. So in the day of clean energy, it's important to know that there are options related to those other alternative energy sources, but they have very, very high limitations in terms of applications. And the further in latitude you move north, the less that option becomes cost-effective and viable. Further south, it's just a little bit easier, right? Pump controls on the left here is a controller we manufacture here in the plant. It's our Geotech environmental control module. On the right is what's called a picocell. It's the conversion device that's used for taking solar and converting it to a standard electric submersible pump. The Geckum, as we call it, weatherproof NEMA 4 enclosure. There's a lot of features. I don't know, John, if you covered that in your session earlier.
No, a little bit. Yeah, it's got a We can put lights on it that tell you when the pump is running or when it's an alarm. There's also an LCD display on the system as well that you can get that information from as well.
And it also, we have a telemetry option. So that's interesting in terms of monitoring system performance. That's something we can talk about as well. PicoCell, standard AC motors, solar power. Having done this for as long as I've been doing this, this is actually quite the innovation because it's pretty easy to acquire and pretty easy to install. It has its own considerations. Variable frequency drive, got some off-grid stuff. Sometimes there's tanker spill or a train derailment. You've got to do some kind of pump and treat in a very remote area. This might be a good option for you. Pump accessories. One of the things that we started manufacturing for the landfill industry, we've got a particular client that deals with landfills, is a cooling shroud. It's designed for side slope risers. It's got some tapered edges. It's easy to deploy a pump and protect it in environments where you may have high sediment loads or other trash or horizontal wells where that may be suitable for the application. There's pressure transducers you can incorporate with these controls. It'll help monitor fluid levels and tell the pumps when to turn on and turn off. Pneumatic pumping systems. Transitioning from electric to pneumatic, each has their advantages and disadvantages. Again, with an electric pump, you've got moving parts, seals, energy consumption. It's usually a little bit more expensive to run electricity than it is to supply air for a whole lot of reasons, but depending on the environment in which the pumps have to be installed, if there's a classified environment, class 1 div 1, class 1 div 2, running electricity is a booger. It's very expensive. But pneumatic, you just got to plumb some pipe with some air, pretty much do whatever you want. There are pumps in the pneumatic realm that are controller-less. They have an internal float mechanism which operates a valve internally. It's a positive displacement type pump. You're applying compressed air to displace the water through the pump, and the float mechanism rises and falls with the fluid level in the pump to actuate the valve. There are pneumatic displacement pumps that can rely on an external controller. The external controller isn't automatic. Automatically, it must be programmed to operate based on the distance and pressure required for the well that you're pumping from. The automatic style pumps with the internal float mechanism require a little more maintenance because there's a few more moving parts. They are a set it and forget it upon installation. As long as you can plumb an air line and a discharge line to the pump, you can pretty much put them down to about 500 feet at the max. But that's a lot of air to take into consideration. When you apply compressed air in a positive displacement pneumatic pump, one of the byproducts of that action is you get a precipitated hard water. So it'll start to crystallize with calcium carbonate, maybe some iron bacteria will start to grow. It can become very maintenance intensive just based on the nature of that type of pump. Factoring in maintenance is a site-by-site consideration. I had a project site in Long Beach Airport in California, and there was so much calcium carbonate in solution that when we would run the water through our air stripper, it would take a 2-inch diameter PVC pipe down to about a pinhole of flow in a month. And it was solid concrete. And air stripping at that time was the best option for that particular site, but the maintenance was almost throw away and start over once a month. Couldn't hardly dissolve the stuff. The only parts that really move in a non-float style pneumatic pump are check valves. So I was saying with the controller, type pump versus the controller-less type pump. There's some advantages within that realm as well. The pump that has the float mechanism, there's more surfaces for precipitates to adhere to, whereas the pump that uses a controller on the surface that's programmable, you only have check valves, 2 check valves in the pump to maintain. So the trade-off is, you know, how much maintenance time and what does that mean on a given site visit as it relates to the pneumatic style pump. On the left is our pneumatic Geckum. It can accommodate up to 8 pumps. The controller-less type float operated pumps are only available in a 4-inch diameter, which will go in a 4-inch larger well. Whereas the type of pump that requires a controller, you can go down to a 1.66-inch diameter pump. About the diameter of a bladder pump. If you have 2-inch wells that are part of your remediation plan, I don't recommend that, but it is what it is, given any given site's already existing wells that may be useful. The pneumatic control variety will give you some options on that. Okay. We also have a pump that's a diaphragm style pump. It relies solely on air, just like the other pumps do. But it is a constant flow for shallow well applications. It relies on suction lift. It does have some flow variability, but as designed, it'll do up to about 4 gallons a minute. So if there's a sump, landfill sump, for example, or elevator sump, or something where you need to remove total fluids and air is convenient to provide, that diaphragm style pump might be an option. We also carry the Blackhawk piston pumps. Piston pumps have been around for a really long time. There's usually a little more effort required in installation. The pump fits on the end of a piston, and the depth of deployment, the rod that controls that piston pump also has to make it to the surface. There's a mechanism on the top of the well that rotates, that moves that piston up and down, just like the old oil wells. You remember the grasshopper looking things? Same kind of principle, but there's some pretty cool features with a piston style pump in a total fluids dissolved phase application. The water is really terrible, it has some viscous or solids. The piston pump will be a good option. 800 feet of pumping depth. A lot of variability in its application. You can actually control the flow rate by augmenting the motor speed. So if it runs dry, you're not worried about things getting damaged. They're very durable. There's a little bit higher cost consideration with respect to piston pumps, but in some cases, if you've got something that's 500 or 600 feet deep, you compare the cost with an electric submersible versus a pneumatic, this might be a good option for total fluids. Now, what to do with what you've pumped, right? You've got the dissolved phase. If it's a hydrocarbon, maybe an oil water separator is a good option for separating out the hydrocarbon aspect of what's being pumped and working with the water that's been cleaned up by the oil water separator through carbon, and then disposing of the hydrocarbons separately. Oil water separators have been around for a long time. Lightweight petroleum products is what they're designed for. They'll take some oily solids and separate those as well. Marine grade aluminum, diffused entries, so you get more surface area to help with collecting the hydrocarbons. They're very efficient. Can you think of anything else to add on that?
We can size them based on your total fluids, what the product is, and based on your flow rate. So there are different sizes based on that. You can add a product storage tank as well.
Yeah, so influent flow rate, concentration of dissolved phase, how large of a recovery feature for the collected hydrocarbons, and then off tank water treatment.
Right, automatic controls, level probes, control panels, transfer pumps, so automatically empty.
Air strippers, has anybody used an air stripper? That old guy in the back. He's my right. Air stripping was very common for a very long time, early parts of the industry growth. They're still very effective. They have a high treatment efficiency based on, again, influent flow, influent concentrations, and chemical constituents. The air stripper, unlike an oil water separator, strips molecules that are not water into a vapor stream, and then you can collect what's stripped in the vapor phase into a carbon or off-gas treatment, such as a thermal oxidizer, a catalytic oxidizer, or something like that. Some things cannot be stripped. Acetone, for example, not a good fit for an air stripper. The Low-Pro line grew out of the development of air stripping from what used to be called a packed tower. So that, going back to that Long Beach Airport example, that was a packed tower air stripper. You have these wiffle ball looking three-dimensional skeleton balls in a column. Spray the water over the top, the balls create a surface area, and you force air up across the water as it cascades down through the column, and what's blown off is your contaminated vapor stream, and what comes out of the effluent is clean water. And it's actually quite astounding how effective air stripping can be. But again, like we talked about with the pneumatic pumps, when you start adding air to a water stream, whatever's in that water stream will start to precipitate out. So packed column towers are very hard to maintain, particularly in hard water environments. So the Low-Pro line was designed to eliminate that. There's a bubble tray. It's a sheet of stainless steel with a lot of holes. And instead of positive pressure, it uses negative pressure. So as the water moves through the column, it's cascading in a counter-rotating measure down through these bubble plates. The air is being drawn through the bubble plates. And if you start getting scaling, you turn the thing off, you let it dry out for a day, kind of twist the metal, the stuff flakes off, and you put it back together and you're good to go. Now there's a couple versions of this. We have a 2 and a 3 version. The 2 is good to 20 GPM.
20 GPM.
And the 3 is good to 65.
60
GPM. They occupy very little floor space. A single person can maintain them with relative ease. And they can be augmented in their capacity by adding or subtracting trays, which is kind of cool. One person can set it up, tear it down. It's got a lot of advantages. So that's a technology that is suitable to your application.
We have a Low-Pro 3 on the floor in the production area.
Oh, okay.
Anybody went through a tour this morning, you probably saw it, but everybody's welcome to go back and we can take a look at it in person if you want to see it.
But how are we doing on time?